Hi, welcome to my channel. Today I'm going to be making a basic tree generator in Python using Blender. And it's not going to have any leaves. I'm just going to do some branching and add some vertices and connect them. So, open a new terminal, change to my working directory. And then I'm going to load this blend file. Basically just has a light and a material for a tree. So I've loaded this load script, and this points to this script, which is just blank. So what I'm going to do is I'm going to start at the origin and move up to create a trunk. And I'm going to separate each node of my mesh by 1 for now. And I'll make the tree 10 meters. Make an empty vert list, empty edge list. And I'll add the origin. And then I'll start a loop. And at each point in this loop, I'm going to add a new vertex to my vertex list. And then I'm just going to connect it to the previous vertex. Then I'm going to update the location. So I'm creating a new vector that has the direction of my direction vector and the magnitude of this float. And then I'm going to update the progress of my loop by adding magnitude. And then I'm going to upload this object. And I'm just gonna not add any polygons for now. I'll just have a bunch of vertices connected by edges. So there's a trunk. It's basically 11 vertices, one at the bottom and one at every 1 meter interval. So the next thing I'm going to do is I'm going to decrease the length of each node as I go up the trunk. So I'm going to add a factor that I want to decrease each node by. Set that to 0.95 for now, and then at the end of each loop I'm going to decrease the magnitude by that amount. So now I've got a few more vertices. I've got 15, and each vertex, it's kind of hard to see. I'll make it a little more dramatic. So there you can see as it goes up the tree, each node gets closer together. And if I set this to 9 and my height is 10, then I actually have an asymptote at 10. If I keep multiplying this by 0.9, I'll actually never reach 10. So when you start to approach this ratio, it can get kind of touchy between like 0.9 and 0.91 is a huge difference. Well, it's an infinite difference. So you want to keep that probably 0.91 at the minimum, and maybe higher. I'll just keep it really low for now, or I mean, keep a low difference. So the next thing I'm going to do is make a probability variable, and that's going to be the probability of starting a new branch. And I'm going to set that to, I guess, 0.8, I'm not sure. So let's see, I'll do this here. I'll generate a random number, and to do that I need to import random. We'll call random.random, and that basically just generates a number between 0 and 1. And then I'll check if that number is greater than some factor of probability, and that factor is going to be magnitude over my original magnitude. So my magnitude is decreasing as I go through the loop, so I'm going to back up my original magnitude here, call it magnitude original. So this represents a factor of my remaining magnitude, and then I'm going to multiply that by this value that I set and check if this random number is greater than that. And if it is greater than that, I'm going to start a new branch. So to start a new branch, I'm going to move in some random angle going out this way in X and Y. So it's going to be random, so I need to seed random again. And this time I want a value between 0 and 360, so I'm going to multiply by 360. Then I'm going to extract the x and the y. Extract the x with cosine, y with sine, and I need to import the math library. And my z is going to be 0. It's going to be at the same height as the point that I branched from. Or, well, this is actually a direction, so I'm basically making a vector that has no height. It points in some x and y according to this random value. So I'm going to call this branch direction, and this is a vector. It's going to be x, y, and z, and it points in some random direction that has no z value. Then what I'm going to do is I'm going to pick a branch length, and that length is going to be some factor of the distance that I have remaining in this loop. So here, if I subtract height, this is the total distance that I have left to travel, and I'm going to subtract my progress, which is distance, and then I'm going to divide by the total height, and this is a ratio between 0 and 1 that represents the progress along the current branch. So I'm going to pass that value onto my new branch, and I'm going to multiply by height. So for example, if my height was 10 and I had progressed 1 unit upwards, say around here somewhere, then my new branch will have a length of 9. So each new branch inherits the distance that it has remaining. So now what I need to do here is I need to generate a new branch, and that's basically going to start this whole process over again. So what I'm going to do is start a new function and call it branch. And branch list is gonna hold a set of parameters. All of these parameters is going to be added to a new entry in a branch list, and then I'm gonna process one element from that list at a time in this function. So first I'm going to make sure the list isn't empty. Make sure it's greater than 0. And I'm just going to copy all of this into my function. Yeah, up to there. Paste that there. And so now when I get to here, I'm going to add a new entry to this branch list. So I'm going to pen a new entry, and I'm going to start with the location. So the location is updated as I'm moving up my trunk, and the new branch is going to inherit that new location. That's basically where the new branch is going to start. I'm going to add my new direction, which is this. I'm going to inherit the old magnitude. So the beginning node of each branch is going to be equal to the previous node moving up the parent branch that spawned it. I'm going to pass my original magnitude because I'm going to use that. I'm going to pass my new updated length. I'm going to pass my decrease factor, which is going to stay the same, and the probability, which is going to stay the same. And so here I'm going to call this function, well, first I need to add my original entry to my branch list. So It's location, direction, magnitude, my original magnitude, my length, and my decrease factor, and my probability. So now I'm going to basically check to see that this branch list has any entries. And actually this is a list of lists, so it should look like this. Each branch is a list, and each new branch is a new entry on the list. So while the length is greater than 0, I'm going to call this function, and I'm going to pass my vert list, and my edge list, and my branch list. And I'm also going to return those. So after I've processed an entry on the list, I'll remove that entry. And then I'll return my lists, vert list, edge list, branch list. And so some of you might be wondering why I don't just call this function again and let it loop recursively. And that's actually how I did it originally. That's kind of a more convenient way to do it, and you don't have to mess with these lists. But I ran into an error where I reached max recursion value and the program just quit on me, so this is kind of my workaround for that. And so I might be ready to try again, so let's just see what happens. Nope. Height. Oh, I need to retrieve all my values. So location, direction, magnitude, original magnitude, Okay, so now I've got a big mess. It's pretty difficult to see what's going on there. So let's make it a little bit easier. And let's break from this loop early. So, I've got several problems here. The first one is that I'm connecting new branches to previous branches. And so to fix that, I don't want to append an edge at every step. There's one step where at the beginning I don't want an edge, basically, because that edge is going to connect to the end of the previous branch. So, well, I want start to be true at first, and then say if start is equal to false, and then start is false. So that's a little bit better. And there's another problem that you can't really see, and that is that these vertices are not connected. It looks like they are, but it's two separate vertices in the same spot. So I'll go ahead and fix that. So let's change this to if not start. Basically the same thing if start is equal to true. I need to take out the vertex that is added at the root of a new branch. So I'm going to also check not start here. Or if the vertex list is equal to 0, so that I won't skip the first point at the beginning of the trunk. So I don't need to append it there. I'll let it append there. And then I want to update my location only. Basically just not at the beginning. So let's try that. No. Let's check. Okay, so I'm gonna remove doubles. Okay, so I don't have any more duplicate vertices, so that's good. Now what I need to do is I had an edge on a new branch that was connecting to the root, but I got rid of that vertex. So I think that's why it's kind of hard to tell what's going on sometimes, but I think that's why I had all those extra connections, because now they're connecting to a new previous vertex, which is not the correct vertex. So I'm trying to fix that. I'm going to make a new variable called root connect, and I want it to be false during the first iteration of the new loop, but then in the second iteration, I'm going to set it equal to true. And then I'm only going to connect if this variable is equal to false. Otherwise, I'm going to connect it to the previous branch. And then set this equal to false. And so vert is not defined, so I need to define that. And that's basically the length of the vertex list at the start of a new branch. So when I first start my tree, that's going to be 0. And then up here I need to update my values. This is now going to be vert. This is the index of the vertex in the vertex list that originates a new branch. And then the other thing I'm going to do is I'm not going to start a new branch at the beginning. I only want to start it at least on the second node, if you're counting the root. So, okay, so that's better. Now my tree is connected like it should be. So what's next? So the next thing I'm going to do is fix this, where I'm picking an X and a Y direction for a new branch to stem from the trunk, which works in that case, but when I start a new branch from like this branch, for example, I don't want it to be an X and Y. I want it to extend in a direction that's normal or orthogonal or perpendicular. There are different ways of saying it. So go ahead and fix that. So I'm going to make a new function. I'm going to call it vector profile. And I'm going to take an angle, and that's a similar idea to what I'm doing here, is generating a random angle and extracting the values, except instead of using those values directly, I'm going to rotate them in the direction of the branch. So I'm going to receive a direction vector, and first I'm going to convert my angle to radians. And then I'm going to extract the values, except instead of extracting X and Y, I'm going to extract Y and Z. And the reason I'm extracting y and z is because I'm going to use this math function called vector2 Euler. And I'll show what that function looks like. So this assumes that a vector pointed in the positive x direction has a rotation of 0. So in order to extract the Euler correctly, I'm going to assume that this direction vector originates in the positive x direction, and that's why I'm using y and z instead of x and y. So then what I'm going to do next is I'm going to rotate those points. X is 0, y and z. And I'm going to rotate it by this Euler, which is basically this direction vector. And then I'll return the new vector. And so to implement that, I'm going to get rid of this. And I'll call my new function vect profile. And I'm going to pass the random angle and the direction vector. And now my new branches are generated orthogonally along the branch instead of always being flat in x and y. So the next thing I'm going to do is I'm going to add some variation to my tree. Here I'm going to generate a new random angle. Whoops. And I'm going to use my vector profile function again to get a normal vector. And that normal vector is going to act as an axis for a quaternion rotation. So the way that this quaternion function works is you have a 3D point, which is another way of saying a 3D vector, and you're gonna, in this function, it rotates this 3D point a certain number of degrees around a certain axis. So that axis is normal to the previous direction. So imagine this is my axis, and imagine this is like a wheel. So I'll make a new circle and rotate it, and pretend that the circle is normal to this. Then if I set rand angle to 4, for example, then my point is going to spin 4 degrees around this point, basically. So I'm basically going to be creating kind of some swiveling or some change in direction at each point to make things look more natural than being completely straight. So see if that, yeah, okay, so now I've got a little bit of bending, so that's definitely better. The next thing I can do is add some random variation in the position of each new vertex. And so this function creates basically a random 3D point in a cube that has a radius of 1, basically. And well, 1 is default, and I'm going to pass magnitude to make magnitude the bounding limits of my randomness. Actually, I'm going to scale it down a little bit. I'm going to scale it down by 2. So I'm generating a random position, and then I'm adding it to my location. So now it's kind of hard to tell with this, so I'll take them both out. So if I take them out, my tree is totally straight. I add in some randomness here. I'm adding in some randomness to the position of each vertex. And this is adding in a randomness to, well, the axis is random. The degree of rotation is not random, but I will randomize that later. So I'm adding in a random direction and a random location, basically. So that kind of smooths out the tree a little bit. You can see this, it looks a little bit rough, kind of boxy. Still looks a little bit boxy, but it is better anyways because I have some bending going on, and that makes it a little more natural. So the next thing I'm going to do is add some bending in the branches as they move up the tree. Instead of sticking straight out, I'm going to define a new axis. So here I'm going to update my direction vector by rotating it, and just as an example, I'll rotate it by 10 degrees. And I'll rotate it around the x vector. And I'll just see what this looks like. So now I've got a drunken tree. Because I'm rotating my branches around the positive x-axis, that's basically spinning my tree. And you can see what happens if I change my axis to the z-axis. Basically kind of twists the tree. So what I'm going to do is I'm going to define a new variable. I'm going to define an axis, and I'm going to set it 0 to start, and I'll add this to my list. And I'm going to create a new branch axis. And I'm going to get that axis by crossing my direction with the z vector. So basically what the cross product does is it finds a vector that is orthogonal to two other vectors. So the cross product of x and y is z, the cross product of y and z is x, because they, well, actually the cross product has a certain order to it. So y and z is y and z is positive x, and z and y is negative x, maybe, or maybe I got that backwards. You can test it. So let's say y is equal to this. Z is equal to this. So let's print math.cross of y and z. And I get the x vector, and if I change the direction, I'll get the negative x vector. So I need to add my axis. And I need to retrieve it. And here I'm going to check that the axis is not equal to the 0 vector. make axis my rotating axis. And okay, so basically by crossing the branch direction with the up vector, I get a vector that's pointed either this way or this way, so I have an axis to rotate the branch around. So as you can see, this is rotating, it's starting to point upwards, and that's because each new iteration is rotating around this new axis that I created. So the next thing I'm going to do is I'm going to distribute the new branches around my trunk a little more evenly, because right now I'm generating a random direction, and if you make your direction random, then more often than not you're going to get a really lopsided tree. So in order to distribute that better, I'm going to make a new function, and I'll call it angle distribute. And I'm going to track each angle on the branch as I go along. So I'll pass a list of angles to check each angle one at a time. I'm going to set this probability value, and basically I'll check, well, so I'll generate a new random number, and I'm going to call this random integer function that generates a random number between the two values that you pass. And then I'll check if this is equal to 0, and if it is equal to 0, then I'll generate a random angle, and so that way every branch won't be distributed, and my tree it won't be too even. You don't want it to be too even, you want it to be a little bit random but not too random. So basically every 1 out of 3 branches is going to be random, and the rest of them will be distributed. So I'm going to seed random, and I need to import random. And I'm going to check if angle list is empty. That means I need to generate a new random angle to start, or I'm going to check if rand is equal to 0, and you could change this to get different randomness, and if either of those are the case, I'm going to generate a new random angle. And if it's not the case, I'm going to basically find the largest gap between all the angles in the list. So the first thing I'm going to do is sort the angle list from lowest to highest using the built-in sorted function. And I'm going to start a loop. And I'm going to look for the index of the angle in the list that has the smallest difference, or I'm sorry, the largest difference between the next angle. So to track the difference, I'm going to make a difference variable, and I'm going to start looping through my list. I'm going to get the difference between the next angle and the current angle. And this tracks the largest amount. So I'm going to check to see if this angle is larger than the current largest. And if it is, I'm going to update the largest. And I'm going to restore the index. And now I need to check one more angle, and that's the angle between the last angle and the first angle. So this is saying if the last angle is not the largest angle, then the largest angle is this. And I'm going to split that difference to get an angle in between. So I'm filling in the gaps between the largest spaces of new branches. And then I'm going to add that to my angle list and return it. And return the angle and the angle list so that I can keep angle list updated. So here at the beginning, I'll start a new angle list for a new branch. And now here I'll let my angle list, or my angle difference, angle distribute function, I'll let that one pick the angle. Angle list equals angle distribute. And angle list equals angle list. So now I need to fix my errors. Mess this up. And this is the difference between the last angle okay, I think that's better. I basically put this line up here. So this is the last angle, and I'm subtracting 360 so that I have a true difference between the first angle, which might be like 10 or 20 or something like that, and some negative angle. Okay, so now in theory I should have a little bit less lopsided of a tree, and the new branches see what happens if I... Okay, that's kind of a mess. But the new branches around a branch that's not the trunk should also be distributed better, because I'm using this angle distribute function to find the new direction of every branch. So the next thing I'm going to do is, rather than have a branch extend from the tree completely horizontally, I'm going to add the option to angle it towards the endpoint of the root branch. So that's pretty easy. All I have to do is rotate the branch around my new axis. So that's basically saying that this branch is going to come out 20 degrees relative to the previous, as opposed to 0 degrees. I would go this way. And the next thing I'll do is, instead of making this constant, this is what's causing my branches to bend upward, I can make it variable. So I'm going to make a new variable. I'm going to define spread, and I'm going to set it to 30 degrees. And spread is going to be the difference of the angle of the starting angle of a new branch from the base to the end. I'm going to define a midpoint, and the midpoint is going to be where the angle becomes 0. So if I have a trunk, I'm going to set my midpoint to be 1/3, about there. And so if I have a 30-degree spread, then I'm going to start pointing downwards by 10 degrees. So I'm going to start like this, and then I'm going to flatten out, and then at this midpoint I'll be even, and then after that my branches will start to curl up, and the degree at which they curl is going to increase. So I'm going to set this midpoint to 1/3. I'm going to get my current progress along the branch, which is just distance over height. It's the distance that I've traveled over the distance, over the total distance. And then I'm going to make a new variable called the bend angle. and I'm going to multiply spread by progress and subtract spread multiplied by the midpoint. And I'm going to pass that. So to start, that'll be 0. No bending where the trunk extends from the ground. And I need to retrieve it. Call it bend angle. And see if I messed this up. I want to implement it here. Okay, so now instead of just being all pointed up, they start pointed down, and then as you move up the tree, they start to point upwards. So next, I can change the distribution of my branch length. So right now I have a linear distribution of branches. So basically as I go up my tree, I get something like this, more or less. Not like that, it's gonna get smaller each time. I can define length to get wider towards the middle and then decrease after the middle. So I'll keep this because I might want either or depending on what I want to do. So I'm going to make a variable, call it linear, or line for linear. Set it equal to true by default. And this corresponds to my linear equation. But if I want a different one, I need to make or progress. No, I already made that. I just need to move it so that it's defined. So I'll move progress here. I'm going to subtract 1. And square this. And then take the root of the whole thing. So this is basically the equation for a circle or a semicircle where 1 is the radius. This would be like your x value if you had y equals 1 minus x minus 1 squared, and this 1 basically shifts it to the right, and then I square that and take the square root. So on a graph, if I have my axis here, it basically looks like this, where this is 1. So I'm going to scale this down, or I could show what happens if I don't scale it down. But then the next thing I'm going to do is put it back into a range that makes sense. To do that, I multiply by height, and I can print this. And instead of using my linear distribution, I'm going to use my spherical distribution. So I'm going to set this to false. And that's what happens when I don't decrease the magnitude, is my branches are now a lot longer, and if my branch length isn't decreasing, then my script's never going to end. So I'll stop that manually and see what happens when I cut it in half. It still takes a lot longer because as you can see, with more length I get more chances for a new branch to form. So I'm going to turn that down a little bit so that it doesn't take as long. Okay, and then next, I think it's almost done. It's almost looking about where I want it. So what I'm going to do now is I'm going to add a bevel. So I'm going to define a new function. I'm going to call it taper. I'll define the radius parameter to be the bevel radius, and the taper is how suddenly I want it to change from one end to the other. And basically I want it to just be like a linear taper. And I'm going to pass a material name, and that's for this material that I already created. So I'm going to add a new curve object, and I'll set the material. And I'm going to back up my context and start a new loop. And I'm going to loop through the vertices in this vertex list. And I'm going to call the curve location function. So this is going to be a branch, basically. It's going to store the location of each node in the branch. And I'm going to iterate through that list. And I'm going to set each section of a curve to the location in the list. So I'll show this curve location function. And does basically what I said. It places this is coordinates the coordinates of the Bezier point given by the past index. It sets it to the location, and it sets the handles to make the curves straight between each point. And if it doesn't, if the length of the index is less than the length of the curve, then it adds a new curve. Or I don't see that actually. Maybe that's here. Yeah, okay. That's the extrude function as it creates a new point. So I'm going to call this function, which straightens the points between the curve. I might have already done that in this function, but I'll do it again. I'm going to add a circle object. This is the bevel. And I'm going to scale it by radius. And then I'm going to set the new object as the bevel of my curve that I created. Now I'm going to make a taper curve. And by default, the curve function deletes all the points of a curve after it creates it, but setting clear to false will keep the 2 points, the 2 original points. Then I'm going to set the taper object. And the second point on the taper handle, I'm going to place with origin. And the first point I'm going to set in -1 in X and negative taper in Y. I'm going to realign the handles, and then I'm going to set my handles. This is the second point. I'm going to set the right handle on the second point. So now I need to implement that. And to do that, I'm going to start a new empty taper list. And as my branch progresses, I'm going to add each new point to my taper list. So since I'm skipping my root, normally I need to come back and fill that in here. So I'll append the location. And do it for the rest of the vertices. And then down here I'll pass my taper list to the taper function. Here. And I'm going to define the bevel radius in terms of the magnitude at the root of the branch. So I'm going to back that value up and then put it in a new variable called magnRoot. And we'll set the bevel radius to half of that. Times 0.5, and then I'll also set the taper according to the root magnitude, and I'll multiply that by 0.5 again, and set my material, which I call bark. So now what I want to do is join all my objects together into one, or I can do that and see if this works first. Okay, so there's my tree has some volume now. It's not extending to the root. I'm not sure what happened. Not equal to 0. Okay. So the next thing I want to do is join all my paper objects together. I'm going to convert the curve to a mesh with a convert function, and then make sure that it worked. I'm going to check, see if the type is a mesh, and then I'm going to dissolve excess geometry. This calls the Blender's limited dissolve function. Selects all the vertices first. And then what I'm going to do is I'm going to name it. I'm going to call it tree. But I only want to name it during the first iteration. So I'm going to make a new variable called trunk. Set trunk equal to true. I'm going to pass trunk to my branch function, and I'm going to return it so that it updates. And then here I need to declare it in a function, trunk equals true, and I need to return it. And here I'm going to check it if trunk is true, then name the object tree, and set trunk equal to false. And if trunk is false, then I want to select the tree object and join the new branch to the current tree mesh. So now when I run this, I get an error because I messed something up. Another error, DPY is not defined in the branch. And now I have one tree object. It's one mesh, and I'm also uploading my original vertex list and my tree. The biggest problem with this script is it's hard to set a correct bevel radius that makes these join smoothly. One thing that you can do is just hope that this doesn't happen or that it's not noticeable, or you can go back and delete stuff like this. Hopefully it's not too much of a problem if your tree is in the background. The next thing I want to show that kind of helps address this is, rather than generate one tree at a time, I'm going to generate a whole bunch at once and then come back and check the results. And to do that, I've made a generator library, and basically what this does is all these different parameters that I defined in my script, I've defined them in a text file, and I've defined them as a range. So height, in my original script I set height to 10. Now I'm going to set it to some value between 4 and 10, and I'm going to let random pick the exact value. And the same for all these values. I'm going to define them as a range, and I'm going to let random pick them. And to actually implement this, I have a make file in my generator folder, and it looks like this. I'm going to call the make function, and I have a list of scripts that I've already made. Here's my tree script that I just showed how to make, and it's not exactly the same, but it's similar. And instead of defining all these variables at the beginning, I'm going to use this function to pass all those values to a script. So here's my tree object. This is a class that I made, and that's here, and I define a prefix. I define where the directory is relative to the generator directory, so it's in this Flora folder. in this tree folder is where I keep, my tree script. So I populate my script list and I pass it to the make. I decide how many files I want. I decide if I want to increment, and the incrementing basically, it stores a unique ID for each object, so that if you need to go back and reference a particular object, then it has a unique ID. So this will just keep incrementing and incrementing so that each new instance has a unique ID. So let's look at the make function. So I'm reading my ID file. And I'm going to start iterating through a loop for each file, and I'm going to retrieve the prefix, the name of the script, and the directory that came from here. This num starts with 0, 0, 0. I'm going to start a new parameter file. So for each of these parameters that I'm choosing a value for, I'm going to store those. And the reason I do that is so that if I generate a tree that I like, then I can retrieve those values. So I'm going to convert those variables to a dictionary. Then I'm going to pass this dictionary to the initialization function, which stores a random value for each entry. And then I'm gonna make a new dictionary for the path to a new blend file that I'm going to open. I'm going to convert the dictionary to a variable so that it can be passed to a script. I'm going to escape the quotation marks, basically same thing as I'm doing here. I'm going to store the number, the prefix, the directory, escape all those variables so that I can pass it to a command line string, which is this. I'm going to start a new command line string where this is the command to execute Blender. I'm going to execute it in batch mode, and I'm going to pass the file path. Then I'm going to convert the script that I retrieved here. I'm going to convert it to a file. To a string. That's basically just going to take this whole script and turn it into a string so that I can pass it to the command line. And then to my command string, I'm going to say that I want a Python expression, which is basically a script that's in the form of a string, which is why I turned this script into a string. I'm going to pass these parameter values that I initialized up here. I need to escape all the quotation marks and add new lines. Then I'm going to print my script, and I'm going to add the line number to each line of the script, and that's so that I can debug variables, because the line numbers in this script are not going to be the same as the line numbers in this Python expression, because I'm adding these variables to the top. So this will help with debugging. And then I'm going to add this save script, which I have on file. And it looks like this, and it's basically going to save my new Blender file. And then I'm going to execute that, and that's basically going to run this script in a new Blender file and then save it. It's going to add this num string, and then I'm going to render it, render an image on file if render is equal to true. So let's go ahead and do that and see what happens. So rather than opening Blender, I'm just going to call Python, because this function is going to execute Blender in batch mode. So I'm just going to call python3 make.py, and hopefully, if there are no errors, it'll add a new file to this out directory. So let's see what happens. So here's the script that I printed with the line numbers. These are the variables that I added to the top, and it's cut off at the end, but this is the dictionary of parameters that came from this parameter file. Then I add my header stuff, and then the actual script from file starts, or I guess the header was part of the script originally. And then this error is a Blender error. I just ignore it. I'm not sure what it means exactly, but there's no real consequences for it. Not for my purposes anyways. And this break printout is, I added a check to my tree script, which checks if this magnitude variable drops below a certain amount, which is like 0.001. So if my distance between nodes gets too small, then I'm not really adding any geometry to my scene. It's just taking up extra time. So I print that I broke, and I break from the loop. That'll exit the current branch and start the new branch. And I have another current branch that checks if my list gets really large. Sometimes a script can take up to several hours for a single tree, and that's if these parameters get set to certain values, like if the probability gets really low or the magnitude decrease gets really low, then a script can take a really long time to finish, and that will prevent that. So after this finishes, if it does finish, maybe it won't finish. Okay, so it did finish. Oh, and it exited. So that's exactly what happened, is this branch list got really large, and so I just quit the script. And then I'm rendering the object in that file, and that's saved to here. It saved this blend file. So let's see what that looks like. So there's my tree that I generated. It's not bad, but it's kind of weird. It's got this curl at the end, which I tried to fix. I tried to fix that here, but it didn't work properly, so I need to figure something else out. So there's my tree object that I created, and here's the image that I rendered. So you could do like 100 of these at once, and you could come back to it in a few hours, and you'll have a bunch of instances, you'll have a bunch of trees, and you could kind of page through them and keep the ones you like. You'll have a lot of trees that aren't really good, and so you just kind of delete them and keep the trees that you like. So I have some examples of some trees that I kept. I set files to 1,000, and I let this run for several hours, and I basically went through and picked my favorite trees, and here are some of them. Some of them have problems. I don't like this. There's too much curl. I tried to fix that, like I said. I still have this problem that I mentioned where the taper doesn't, or the bevel doesn't join the branch properly, and you can fix that manually. You can go back and delete the extra geometry, but I mean, you can also just leave it. These trees are, honestly, they're not going to be the best. This program is kind of a work in progress, but at least you got to see the process. And the kind of main point is this function where you can kind of batch generate these things. And the other nice thing is that you have, for each new tree, you have a parameter file. So if you find a particular tree that you like, then this tree can become a kind of a parent tree. And or a better example would be something like this is one of my favorite trees, or maybe this one is not bad. So if I wanted this to be a parent tree, I can retrieve these values and use them as a new center to spawn new trees. So you can kind of make new kind of quote-unquote generation of trees. So you're kind of growing trees, kind of literally, figuratively growing trees on your computer, because they can kind of evolve. A lot of them will be junk and you'll just kind of throw them away, but some of them can form a new quote-unquote generation. So that's pretty much all I wanted to talk about for that tree. I do have another kind of algorithm, if you want to call it that I can show. It kind of takes a different approach. The result is not as good, and I'll show you some of these trees. They're not as natural looking as the ones I just showed, but I can still show kind of the process for this new tree. And basically what I do for that one is I create a sphere and add a bunch of points to the sphere, and then I create another concentric sphere inside that, and this sphere will have fewer points. So then what I do is I join the points from this outermost sphere into the nearest innermost sphere, so you get kind of this branching effect. And I can show what that script looks like. That's the wrong folder, obviously. It's in here. So here I'm making a bunch of spheres by calling this sphere function. And that looks like this. I'm basically generating a sphere from scratch. and I have this distribution circle variable. Or I can just show what this does. So I'll save this in my generator folder. And I'll make a new script. I'll call it sphere. And get rid of all of this. So that'll generate a new sphere, basically in the same way that, or it has pretty much similar, if not identical, geometry to Blender's sphere. But if you set this distribution parameter to false, then it changes the way I forgot to reload. This is why I use a loader script. So it changes the distribution of these rings to be linear instead of like this where the rings get closer together, and that just it makes for a more even distribution of branches. So in here I connect these shells, I track the position of each shell, and then I make a new curve that starts at the outside and it finds the closest point in the next inner shell, and then it kind of zigzags towards that point so that the branches are a little more natural looking, and then it does adds a taper and a bevel similar to what I just showed, and then uploads it. So that's kind of a different strategy. It starts on the outside and works its way in, as opposed to this one which starts at the bottom and works its way out. So I have another set of tree scripts that I generated using geometry nodes, and they're kind of these conifer type trees, and I'm not going to show that because it's a big mess and because this video is long enough, but I might make like a trees part 2 video where I show how to do this if I clean up this file a little bit. And the reason I wanted to show this is because I use a node that selects polygons by area, and that's how I position these pine needles on the ends of these branches. I add more needles if the area is less. So you could do a similar thing if you wanted to add leaves to these trees. But I'll save that for later. And I think that's basically all I wanted to talk about, so I hope you enjoyed the video, and thanks for watching.